Hi everybody, my name is Luca Shar. I'm an undergraduate at UCSB and I'm going to talk about the theoretical work that I've been doing with Mark Bowick, Christina Marchetti, and Suraj Shankar on spatial control of topological defects in active pneumatics through activity patterning. So, a bit of a refresher, pneumatic liquid crystals with high activity exhibit spatiotemporally chaotic flows, often referred to as active turbulence. These states of active turbulence are characterized by the proliferation of topological defects of strength +1/2 and -1/2, with the +1/2 defects being self-propelled with a velocity which is proportional to the magnitude of the activity. This is generic behavior. It's been found in a wide variety of experimental realizations of active pneumatics. Now, topological defects are intimately connected to the underlying active flows of the pneumatic. So if we can understand and control defects, we gain control over these active flows. This could have potential applications of things like active microfluidic devices. There's been a lot of recent work on different methods for controlling defects. These include things like tuning the structural and material properties of the substrate that the pneumatic lies on, frustrating the pneumatic order by physically confining it with controllable boundary conditions, or by placing it on a curved substrate. And recently, with the advent of light-powered active matter systems, has come a new method for controlling defects by spatially patterning the activity of the pneumatic itself. We've been using a combination of computer simulations and analytical theory to explore novel defect dynamics in systems with spatially patterned activity. We used simulations to numerically solve the well-established two-dimensional pneumatodynamic equations in terms of the pneumatic's flow velocity field U and its tensor order parameter Q. The first equation here describes the dynamics of Q in terms of relaxation of a Landau-de Gennes free energy, and a flow coupling term S involving both Q and U. We assume flow is generally slow enough to be non-inertial, so the second equation is a Stokes flow equation, including substrate friction, viscosity, and an active stress term. Usually, the activity, alpha, is a constant and left outside of the divergence. But since we're studying systems with spatially varying activity, it becomes a function of position and has to be brought inside the divergence term. The first thing that we were interested in exploring with these simulations was how defects behaved in regions with non-zero gradients in the activity. So we simulated an active strip, where we varied the activity only along the x direction, with a highly active region in the center, surrounded on both sides by regions of zero activity, separated by interfaces of controllable width Wi. By tuning Wi, we control the sharpness of the activity gradient at the two interfaces. The first regime that we looked into using these simulations was how weak gradients in activity affect defects, so strips with very wide interfaces. We ran these simulations with random initial conditions and then looked at the steady-state behavior of defects by averaging their positions over time and along the y direction, where the activity doesn't vary. What we found was a steady-state topological charge separation of defects along the activity gradients at the interfaces of the strip. This plot on the left shows the time and y-averaged defect density distributions, where the solid blue line shows the +1/2 defect density, the solid red line shows the -1/2 density, and the dashed black line is their sum, the total defect density. We can see that for these weak gradient interfaces, the +1/2 defects accumulate on the outside of the active strip, closer to the passive regions, while -1/2 defects accumulate closer to the center of the strip. You can also see this effect by just looking at the simulations shown in this video on the right, where we can see these +1/2 defects extending out towards the passive regions, with their polarizations oriented up along the activity gradient. This is fairly intuitive behavior. We know that +1/2 defects act kind of like self-propelled particles, and self-propelled particles tend to accumulate where they move more slowly. What's surprising from this point of view is what happens when we decrease the width of the interfaces and make the gradient sharper. For sharper activity gradients, we see very different behavior. +1/2 defects no longer escape the strip and extend out into the passive region. Just looking at the simulation, it's difficult to see any detailed steady-state behavior with the naked eye, but if we time and y-average the defect distributions in the same way as before, we can actually see that sharp gradients also induce a net topological charge separation along the gradient. But the dipole now points in the opposite direction. +1/2 defects now accumulate closer to the center of the strip than -1/2 defects. We repeated these simulations varying both the magnitude of the activity and the width of the interface. We can calculate the time-averaged net topological charge distribution, ρ, by subtracting the +1/2 and -1/2 defect density distributions. and then we can calculate the dipole moment across an interface by integrating that charge distribution over half the simulation area. A positive dipole moment means that +1/2 defects are extending outside of the active strip into the passive region, while the negative dipole moment means that +1/2 defects accumulate closer to the center of the strip, with -1/2 defects staying closer to the edge of the interface. Here we've plotted the dipole moment as a function of the magnitude of activity gradient, and we found that the sign of the dipole moment flips above a finite value, about 0.2 in the units of our simulations. This dipole flip transition is pretty unintuitive in our previous picture of +1/2 defects as simple self-propelled particles accumulating where they slow down. In order to understand this dipole flip, we apply a hydrodynamic theory of active topological defects developed by Christina Marchetti and Suraj Shankar in 2019. This theory arises from treating defects as an active Coulomb gas of self-propelled positively charged particles and passive negatively charged particles, and describes the large-scale flows and behavior of defects in terms of a few hydrodynamic fields, like the total defect number density n, the topological charge density ρ, and the polarization of +1/2 defects p. An important feature of this theory arises from a topological constraint, which relates gradients in the phase of the nematic order parameter to the topological charge density ρ. This essentially results in an analog to Gauss's law, where we can relate the charge density to the divergence of an electric field, which we can see to be the rotated phase gradient, where epsilon here is the two-dimensional Levi-Civita tensor. So, phase gradients, which as we'll see can arise from spatial patterns of activity, act like electric fields and drive defect motion. We then apply this hydrodynamic theory to the case of our active strip. Activity enters by assuming that the steady-state defect density n is directly proportional to the magnitude of the activity alpha, as is the self-propulsion velocity of +1/2 defects. We found both of these assumptions to match what we see in our simulations very well. Plugging our active strip activity profiles into the linearized steady-state version of this hydrodynamic theory, we were able to find analytical solutions for the steady-state charge density ρ of x in the limiting cases of a weak gradient in activity and an infinitely sharp gradient. These analytical solutions for the charge density reproduce the flip in dipole moment between shallow and sharp activity gradients. Comparing the analytical solutions to our numerically calculated charge distributions, where we've roughly fitted them to match the numerical solutions at their maximum values, we see a pretty good qualitative match for both the weak and sharp activity gradients. For a weak gradient limit, when the interface widths are large, we can neglect defect diffusion terms in comparison to ballistic motion over the width of the interface. This greatly simplifies the steady-state hydrodynamic equations and allows us to find a general closed-form solution for arbitrary activity profiles. This solution also provides us with the insight that gradients in the squared magnitude of the activity induce transverse phase gradients, which in turn act like electric fields on defects. So we see that activity gradients also act like electric fields, with constant gradient areas sorting defects by their topological charge. In our sharp gradient limit, the interface is narrow enough that defect diffusion terms can't be neglected. So an analytical solution to the hydrodynamic equations only becomes possible for a step function activity profile with infinitely sharp gradients. Numerical calculations will be required to apply this theory to general sharp activity gradients, which is something that we are actively working on. Other future directions that we're working towards include trying to see if we can understand activity gradients as an effective force or torque on defects. Our approach towards this goal right now involves using a circle of activity to trap two +1/2 defects together and to vary the gradient to try to compare its effective force with the Coulomb repulsion between defects. We also plan to continue to push the limits of the electrodynamics analogy. We're interested in seeing if we can use activity patterning to build essentially topological electronics. We also plan to look into systems with spatio-temporally varying activity, potentially looking for things like coherent flowing states of defects in traveling activity waves. Thank you so much.